Samile Gao is also from University of Queensland. We'll talk about balanced hole and electron transport in TCTA ERPI blends as determined by Photo-MIS-CELIV. So if you would like to give your presentation when you're ready, please.
Okay, thanks, Bronson, and good afternoon, everyone. The title of my talk today is Balanced Hole and Electron Transport in TCTA ERPI blends as determined by Photo-MIS-CELIV. First, a little background about how a typical OLED operates. We have charge injection, then transport and recombination to radiate light. But if the charge transport for holes and electrons is not balanced, say if we have excessive holes, they will accumulate, leading to lower efficiency, unpreferred recombination zone, and short device lifetimes. So to achieve optimum device performance, it is crucial to know what's the mobility of each charges. With the charge mobility preferably measured in a device configuration that is similar to an OLED. There are a number of mobility measurement techniques: the time of flight, the space charge limited currents, or the organic field effect transistors. But the time of flight, it requires a very thick sample. And for the SCLC, the selection of the electrodes with the most suitable work function might be difficult. As for the field effect transistors, due to the very high concentration of charge carriers in the conducting channel, the mobility measured might not be relevant to an operational OLED device. So we choose the MIS-CELIV, which was chosen for its advantages to selectively measure both the electron and hole mobility in a diode structure close to an operational OLED. Here is a schematic of the MIS-CELIV setup and for the electron mobility measurement. The device is connected with a function generator, oscilloscope, and external attached resistance. When we first applied a small offset voltage, will act as a normal capacitor with charges injected and reach a stable status. And at this time, the capacitance is fully charged. Ideally, there should be no current detected from the oscilloscope. And then we increase the voltage. The charges will be extracted steadily, forming an extraction current. And when the voltage drops to offset again, the device is recharged and stabilized again. So the current becomes zero again. But what if we apply a sufficiently large offset at the beginning? If it's large enough due to the increase of electric field, some of the electrons will be injected through the semiconductor layer and reach the interface of the organic and insulator layer until an equilibrium was reached. And at this time, no current should be detected. Then, with a linearly increasing voltage, these accumulated electrons will be extracted and forming an extraction transient. And when the voltage drops to offset, the device reaches a stable status again. And in the case of the small extraction, the time it takes for the current to reach the maximum is defined as a transit time. And with this transit time, we can work out the mobility. MIS-CELIV was successfully used to measure the hole mobility of the common host material, TCTA, and blend films with different doping ratios of ERPI. However, since the charges are injected from the electrode, it is not always possible to find the electrode materials that enable efficient charge injection under experimental conditions. To solve this problem, we've come up with an alternative way, that is to use photo-generated charges within this organic film. So we turned to the Photo-MIS-CELIV, where charge carriers are photo-generated inside rather than injected from outside. The setup is quite similar, and the only difference is that a UV LED was introduced. In the case of an electron mobility measurement, the function generator was connected to the aluminum electrode, and a negative bias is then applied for the light duration period, which drives the photo-generated electrons to the insulator and organic semiconductor interface, and they will accumulate due to the charge blocking of the insulator. At the end of the light duration period, the LED was switched off, and a linearly increasing voltage changes the electric field, leading to the extraction of the accumulated electrons. It can be envisaged that if the output is connected to the ITO side and other experimental parameters are kept the same, holes will accumulate rather than electrons. And by analyzing the position of the extraction peak, we can work out what the mobility is. So the Photo-MIS-CELIV method allows us to measure both hole and electron mobility in the same device by simply switching the polarity of the function generator, regardless of whether an electrode has a poor ohmic contact or not. To validate this method, we first measured the charge transport property of a neat ERP film. The electron mobility of ERP has not been measured and is not measurable using standard MIS-CELIV due to the injection problem. And these are the resultant transients for both hole, which is the red signal, and electron mobility, which is the blue signal. We can see that both transients have well-defined peaks, and the hole mobility and electron mobility can be calculated to be 2.3 and 3.2 times 10 to the minus 5. The value of the measured hole mobility was close to the previously reported value, which gives us the confidence in this method. And the more interesting result is that the RP does have a measurable electron mobility. And this mobility is similar in the magnitude to its hole mobility. But there might be argued that when you're measuring the electron mobility, you're not measuring the extracted electron, but measuring the injected holes. So you get to similar numbers. But this is not the case since the use of aluminum electrode. Aluminum electrode is blocking hole injection. And more importantly, we have another evidence where we undertook the Photo-MIS-CELIV measurements on neat films of TCTA, which is known as a hole transporting material and can be used as electron blocking material for OLEDs. It has very low electron mobility, but very good hole mobility. And as expected, we have a clear transients for the electron of holes, but there was no signal for the extraction of electron. Even when the pulse duration was increased to 100 microseconds, the transient is still flat. So we can conclude that the electron mobility of TCTA has to be less than 10 to the minus 8, which agrees with previous reports that TCTA has negligible electron mobility. And this is also an evidence that aluminum is effective in blocking the hole injection. Otherwise, either injection or extraction, there must be some hole signal for the blue line. So from these measurements, it can be concluded that Photo-MIS-CELIV can selectively and reliably measure both the hole and electron mobilities. But there in the measurement, there's a couple of parameters that can be varied, namely the light duration, which is the time the film is exposed to the light, and the delay time, which is the time between turning off the light source and start of the linearly increasing voltage. So we measured the hole mobility of neat ERP films utilizing a range of delay times, which is shown in the left figure, and the range of light durations shown in the right figure. From the left figure, we can see that it is apparent the magnitude of signal decreased with the increasing delay time. This is reasonable given that increasing the delay time increases the probability of recombination and leakage of the photo-generated charges. So for Photo-MIS-CELIV, we should ensure that the delay time should be minimized to increase the signal intensity for ease of analysis. For varied light durations, the transient signal increased up to a light duration of around 2 milliseconds, and then it became saturated. What's more, it was also found that the transient peak shifted to slightly shorter times. So it's important that the films are illuminated for sufficient length of time to saturate the signal and avoid an underestimation of the mobility. So now, with the understanding of the effect of different parameters, we finally applied the Photo-MIS-CELIV to measure the hole and electron mobilities of ERP TCTA blend films. For reference, the hole mobilities of equivalent blends obtained using standard MIS-CELIV, which is the green dots here, they're also included for reference. We can see that the hole mobilities obtained from Photo-MIS-CELIV, which is a red one, they follow the same trend as those measured using MIS-CELIV, which significantly decrease from the neat TCTA film when RP was blended at 10 weight%, and then increase with increasing the RP concentration. The reason for this increase are the formation of RP-based pathways for hole transport and a reduction of the number of hole traps. It is interesting to note that the trend in the electron mobility, which is the blue dots, they're almost similar to the trend of the hole mobility, irrespective of the doping ratios. So this is an indication of that in the blend films, the transport of the holes and electrons occurs primarily on the RP molecules, with TCTA only playing a minor role. And this result provides good evidence as to why OLEDs containing these materials can have very high efficiency. That is, this combination of materials have a very good high PLQY, and they have balanced the charge transport. Finally, another potential application of Photo-MIS-CELIV, we can use it to calculate the quantity of photo-generated charges. And I believe this is more important for organic photovoltaic blends. By integrating the transients over the time, we can calculate the quantity of photo-generated holes under different light durations, which is shown in the right figure. We can see that increasing the light duration led to an increased number of photo-generated holes. And finally, they saturated. The number of absorbed photons can also be worked out. If you have the energy of a single photon and the total energy absorbed by the film. Therefore, the quantum efficiency can be calculated. And following this method, the quantum efficiency of RP was calculated to be 0.07% in this case from the 10 millisecond transient. The conclusion, Photo-MIS-CELIV can be used to measure the electron and hole mobilities of organic semiconductor knit and blend films using a single device architecture. And optimize the Photo-MIS-CELIV should use minimal delay time and long enough light duration. Finally, the RP TCTA blend films, they were found to have balanced the charge transport. I would like to thank my supervisors, Professor Paul and Dr. Amantas, and thank you everyone for your attention. Thank you.
Thank you very much. We'll open up for questions from the audience. Does anyone have any questions?
Hi, I'm Sid.
Go ahead. Go ahead, Sid.
Hi, Mile. Nice presentation. I really like the work. Just had one thought. Can you comment on the role of intensity of incident light on the measurements you'd be getting, the mobility measurements?
Oh, you mean the incident light, the effect of incident light?
The intensity of incident light, how significantly will it impact the mobility?
Yeah, this is a very good point, and I believe that's my next step, because in this measurement, I just have, it's like a trial of this method. So I didn't vary the intensity of the light, and also I don't have the device set up. I only have one LED. So yeah, but in the next step, there's lots of tricks we can play, like vary the intensity of the light. We can vary the wavelength of light, and also we can put the device under one standard set to see how the quantum efficiency we calculate, and also the mobility. So for your question, I don't sorry, I don't have the data available for you at the moment, but I will do that in the next step.
All right. Okay. Thanks, Mile.
Were there any other questions from our audience? If not, I might quickly ask, I see you have a different mobility calculated using MIS-CELIV versus Photo-MIS-CELIV. Even though these are quite similar techniques, can you comment a little bit on why there would be this difference?
The difference, I believe the difference, the reason of this difference can be many, because one, we are measuring the extraction of the injected charges. The other, we measure the photo-generated charges. And also, if we look at this data in, I didn't plot the errors, but if you include the errors, you can see that the values are actually very close. And given in the magnitude of the measurements, I believe these two techniques, their results are pretty similar. But if you compare with other techniques, for example, time of flight, SCLC, there might be a difference, several times difference. So from my point of view, I think these results are quite close.
Yeah, excellent. Thank you. Okay, last chance if anyone has any other questions. If not, then thank you very much, Mile, very interesting talk. And so we will